Hey there, and welcome to this explainer. Today, we are diving into an absolutely mind-bending reality of our universe, a quantum trick that completely, totally defies the everyday physics we're all used to. We're going to explore quantum tunneling, which is this fascinating, honestly bizarre phenomenon where particles literally pass through impossible walls. Let's just start with a super simple question. What happens when you throw a tennis ball at a solid brick wall? I really want you to imagine this familiar, everyday macroscopic scenario. You've got a heavy, solid wall, a bouncy ball, and you wind up and throw it as hard as you possibly can.
Yeah, obviously it bounces right back. Our everyday intuition is totally spot on here. It confirms that without literally breaking the wall to pieces, going all the way around it, or finding some random hole passing straight through solid matter is, well, it's impossible. Right? But what if that ball just suddenly appeared on the exact opposite side? In our day-to-day lives, no way, that's impossible. But down in the quantum world, this incredible phenomenon happens all the time.
Section 1, the classical physics trap.
Okay, so to really appreciate how wild quantum mechanics is, we kind of have to look at the strict limitations of our classical world first. Think about, riding a bike up a really steep hill. If you don't pedal hard enough to get sufficient speed, you're just going to roll right back down. That is classical physics in a nutshell. Objects absolutely need enough energy to climb over a physical barrier, period. The same rule applies to balls, cars, rockets, you name it. But then you have quantum mechanics. Under these rules, particles can just mysteriously appear on the other side of a barrier. This tells us that tiny entities like electrons just flat out ignore the everyday rules we're used to.
Section 2, particles behaving like waves. So what is the secret behind this physics-defying magic trick? Well, it turns out quantum entities aren't actually tiny, solid little balls. Instead, they are defined by what's called a wave function. This is essentially the mathematical description of a quantum particle, representing it as a wave of probability rather than a hard, solid object. So when this probability wave reaches a physical barrier, it doesn't just smash into it and stop instantly like our tennis ball does. Part of that wave actually bleeds into the barrier itself. And this leads us directly to the concept of quantum tunneling. This is the phenomenon where quantum mechanics predicts a non-zero probability of finding a particle beyond a barrier that it classically shouldn't be able to cross. The really crucial thing to grasp here is that the particle isn't like drilling a tiny hole through the wall. It isn't casting a teleportation spell. Instead, because a part of its probability wave extends beyond that barrier, there is a very real, actual chance you'll detect the particle on the other side.
Section 3, the Schrödinger Equation.
Let's actually break down the math that dictates this bizarre wave behavior step by step. Step 1, the quantum wave reaches the barrier. Okay, pretty straightforward. Then, step 2 is where it gets fascinating. The wave decreases exponentially inside the barrier. Notice it doesn't just instantly drop to zero, it just rapidly fades. Finally, step 3, if the conditions are just right, a surviving fraction of that wave emerges on the far side. And if enough of that wave makes it across, boom, the particle can emerge there too. Think of it kind of like a voice becoming quieter as it passes through a thick wall. The quantum wave becomes weaker inside the barrier. Imagine you're standing outside a massive, super thick concrete wall, and someone is shouting from the other side. Eventually, the wall is so thick that the sound just fades to absolutely nothing. This perfectly explains why thicker, taller barriers make tunneling virtually impossible for everyday objects, but highly probable for tiny particles moving through incredibly thin barriers.
Section 4, powering the sun.
Okay, let's shift gears from all this abstract math to the massive cosmic scale of our very own solar system, because this shows exactly why this whole thing matters. Consider this astonishing comparison. Under our classical expectations, hydrogen nuclei, which are positively charged, strongly repel each other. Even at the completely extreme temperatures cooking inside the sun's core, classical physics says many of these nuclei simply shouldn't have enough energy to get close enough to actually fuse together. But check out the quantum reality. Nuclei actually tunnel through that energy barrier, and nuclear fusion ignites. This releases just enormous amounts of energy. Basically, every single sunrise you have ever seen exists strictly because of quantum tunneling. How wild is that?
Section 5, the tech in your pocket.
And this brilliantly illustrates that this phenomenon isn't just some fascinating cosmic theory for stars millions of miles away. Scientists use quantum tunneling in everyday tech right now. It's used in scanning tunneling microscopes to literally image individual atoms.
but it's also sitting right in the flash memory of your USB drives and SSDs, standard semiconductor devices, and for sure in cutting-edge quantum computing research. It even plays a huge role in radioactive decay. The big takeaway here? Without quantum tunneling, modern electronics and smartphones simply wouldn't function at all. Quantum mechanics is incredibly practical, and you literally carry it around in your pocket every day.
Section 6. Can humans walk through walls? So you might be wondering, if tunneling is a totally routine event for electrons, could you tunnel through a concrete wall? Well, according to the strict rules of quantum mechanics, the probability isn't exactly zero. But when you calculate the staggering numbers, the wait time required to actually observe this happening is far, far longer than the entire age of the universe. For massive objects like us humans, the probability of our complex wave functions making it completely through a thick barrier is so unimaginably tiny that it is effectively zero. So yeah, while tunneling is an everyday thing for electrons, I really wouldn't suggest trying to walk through concrete anytime soon.
As we wrap up this explainer, I want to leave you with this really powerful thought. The impossible is only impossible until quantum physics enters the picture. Quantum tunneling teaches us that nature behaves in ways that entirely defy our everyday intuition, literally powering our sun and driving our modern technology. If particles can routinely break the rules and walk through impossible walls, what other impossible